single variable. However, there are very rare situations in which we have to deal with a data on a single variable. Most of the times, in any statistical analysis, data you are dealing with mainly the exploratory part of data analysis, one variable whenever we are coming across. So, suppose we are dealing with two or more variables at a time which seem to be related with each other, then are there any statistical techniques to get the insight of the behavior of the two variables, and if they are, which are they, and how can we measure the strength of the relationship between the two or more variables? All these questions come under the purview of correlation and regression analysis. So, we will begin with the correlation analysis in today's session. We will deal with the concept of correlation analysis, when should we use it, the crude way of getting some idea about the interrelation between the variables through scatter plot, which are the different types of scatter plots and what do they convey to us, and what is the correlation coefficient, which is a measure for getting the extent of relationship between two variables. We will be focusing today only on two variables. The concept can be extended to more than two variables in multiple correlation and multiple regression, which we are not covering in this course, or at least in this particular lecture. So, the correlation coefficient and its merits and demerits. This forms the agenda for today's session. Okay. So, we have interest in studying the relationship between two variables. For example, suppose we want to know how the two variables, age of the patient and systolic blood pressure, vary together. Then we are interested in the correlation between the age of the patient and the systolic blood pressure. So, in such cases, we want to quantify the relationship between the variables. We can say that the systolic blood pressure increases as age increases. So, this is kind of qualitative statement, but how much and what is the degree? In order to answer that question, we have to quantify the correlation between the two variables under consideration. So, that is what we try to measure in the correlation analysis. Now, why do we need correlation analysis? Because they are useful, first of all, in giving us the idea about the association between two or more variables, and they can also indicate a kind of predictive relationship between the two variables, in which one of the variables could be a cause and the other could be an effect, although it may not be necessarily so in all the situations. They help understand whether the relationship is positive or negative. By that we mean that if one variable increases, the other also increase, then we call that the relationship is of positive nature. Height increases, weight of the person increases, so height and weight can be considered as positively correlated. We will see the details of this type of relationship and the different types of relationships in due course of time. As I mentioned that although they can be used to indicate the predictive relationship, there need not be necessarily always a causal relationship between the two variables. Some of the examples of two variables where they are associated with each other are as follows: physical stature of parents and their offsprings, demand of a product and the price of that product. When should we use the correlation analysis? Whenever we feel that the two variables are interrelated. And even though we feel that the two variables are interrelated, we have to first of all explore whether they are interrelated or not. And then after knowing that they seem to be interrelated, then we would like to measure the extent of the relationship between the two variables. So, one way of exploring or finding out whether the two variables are associated with each other or not. Here I would like to emphasize that although we are calling as any two variables, the correlation analysis or correlation coefficient mainly is used whenever you are having the continuous or ratio type of variables, interval type of variables, or at the most the categorical variables. For the qualitative type of variables, we have different measures of association which we are not considering right now. So, we are considering here that the variables are of continuous nature, and then suppose we plot them in a scatter plot. So, as there are two variables, suppose x is the height and y is the weight of the person, then and you have n individuals. So, you have measured the heights of these n people and the weights of those n people, and they are stored as y1, y2, yn. So, obviously the data are in pairs. For the same person you have x value and y value. So, it is called as a bivariate data. So, x1, y1, x2, y2, x3, y3 and xn, yn are the bivariate data on two variables x and y. If you consider these two variables on a graph and plot them, you can take one variable on x axis and another variable on y axis, and then you get a scatter plot. And with the help of scatter plot, we get a general idea about the existence of the correlation and type of such correlation. We will see some examples of scatter plots. Pictorially, if suppose you have plotted x variable on this axis, y variable on this, and each of these is a data point corresponding to those x and y coordinates, and then you see that the points are, the pattern in the points is shown like this. So, here you observe that the smaller values of x are associated with the smaller values of y, larger values of x are associated with the larger values of y, and there is a tendency among the points to cluster around some central line which is not yet there, which we will compute whenever we will go in for the study of regression. But they seem to be clustering around some hypothetical line. Then what do we observe here? We observe here that there is a kind of linear relationship between the two variables x and y. The two variables in this case are said to be strongly positively correlated. On the other hand, here also you see the similar type of behavior, that the smaller values of x are linked with the smaller values of y, larger values of x are linked with the larger values of y. So, there is a positive correlation, but that is not that tight as it is depicted in the first figure. There is a more variation between the data points, and then this is a positive correlation, but the correlation is weak. Similar situations are explained here with the reverse strained. So, x on x axis, y on y axis. Now, if you look at this particular data point, then its x value is very small, but its y value is very high. So, smaller values of x are associated with the larger values of y, and as you increase x, as you increase the values of x, the value in y decreases, or the larger values of x variable are linked with the smaller values of y. So, there exactly is the reverse tendency between the two variables, and this is a case of negative correlation. Now, why it is called strong negative? Again, there is a less joint variation among all these points. They are pretty tight around a straight line. So, there is a linear relationship and the relationship is pretty tight. So, this is a case of strong negative correlation. On the other hand, one can explain that the trend is negative, but the correlation is not that tight, and therefore it is a case of weak negative correlation. Here it can be moderate, it can be this very small. Now look at this particular scatter diagram. Here you see that the number of y points for smaller values of x, you will get the similar number of y points for large values of y values for the larger values of x. So, you do not see any such kind of trend in the two variables. So, it is like that these two variables are not dependent on each other, they are behaving in their own manner, and therefore, there is an absence of correlation. So, the word itself is self-explanatory, it has to be correlation, the relation between the two variables. So, the point is that you can get an idea from looking at the scatter plot about whether there is a correlation or not. So, about the existence of correlation as well as the direction of correlation. But you cannot get the idea how much, you have to answer the question objectively, how much is the correlation between the two variables. That is provided by coefficient of correlation, which is called the linear correlation coefficient. Now, why it is linear correlation coefficient and all that, that we will see little later. So, we will study now the measures of statistical correlation, the correlation coefficient, which measures the strength as well as the direction of a linear relationship between the two variables under consideration. It is invented by Carl Pearson, and that is why it is known as Pearson's product moment correlation coefficient. Now, the mathematical formula for computing this correlation coefficient looks scary, but it is not like that, and you do not have to remember it by heart as well. I will try to give you a gist of why this is the formula in due course of time. So, let us proceed further with the presentation. The correlation coefficient value ranges between -1 and +1. One has to have a limit for the correlation coefficient, whichever measure you are computing. If you do not have the limit, then it is very difficult to compare two data sets. Okay. So, the limit for the range for the correlation coefficient is from -1 to +1. Obviously, when you have +1, then that means it is the maximum positive correlation between the two variables. It also indicates a perfect positive fit. So it is like y equal to 3x plus 5. You can find out a formula between y and x which is of linear type, and then the correlation coefficient will be equal to plus 1. Similarly, the correlation coefficient equal to minus 1, it can be a formula like y equal to minus 3x plus 5. Okay. So as x increases, y is going to decrease with a exact, you can have an exact formula. So perfect negative fit, and then you have a perfect negative correlation. If there is no linear correlation or a weak linear correlation, R is close to 0. This implies that there is a random non-linear relationship between the two variables. R is a dimensionless quantity that is independent of units. That is very important, and why it is so I will explain to you with the help of a diagram in Excel. As I mentioned, R equal to plus or minus 1 occurs only when all the data points lie exactly on the straight line. R equal to plus 1, the slope of this line is positive. R equal to minus 1, the slope of this line is negative. Value of R greater than 0.8 implies strong correlation. So it can be either a strong positive correlation or strong negative correlation if you have R less than minus 0.8. R less than 0.5 implies weak correlation, and R equal to 0 is no correlation. Now before moving in for the next slides, I would like to show to you some examples or some situations where we can get an idea of the scatter diagram as well as the correlation coefficient. Here there is a fictitious data of height of father in centimeters and height of sons, of elder sons you can say. And then you suppose you plot this data in Excel, you get this kind of scatter diagram. Now what do you observe here? Do you observe any such kind of positive trend, positive relationship between the two variables? The point here is that if you ignore this particular data point, you will definitely see a kind of positive trend between the two variables. So, it is very difficult to judge if there is any positive correlation between height of son and height of father by looking at the scatter diagram. So, if you compute the correlation coefficient in Excel, it turns out to be equal to 0.3267. So, the point is that there is a positive correlation between the two variables, but it is not very strong. It is a kind of weak positive correlation between the two variables. Here is another example taken from the same data which I was explaining at the time of dispersion. The survival in months in the multiple myeloma study and the lymphocyte variable. So, if you plot these two variables in a scatter plot, you get this kind of picture. Again, just like this, looking at the scatter diagram, we may or we may not conclude that there is a positive correlation between the two variables. What does the data say? If we compute the correlation coefficient, the value is equal to 0.058. So, which is very close to 0. So, there does not seem to be a significant correlation between the two variables, survival in months and the lymphocyte. Now, all the answers to the underlying study cannot be just obtained by computing the correlation coefficient. There are further statistical methods. For example, whether this value 0.058 is close to 0 or is not close to 0. Should we consider that these two variables are not correlated or they are correlated? So, these kind of questions we answer in statistical inference. One should be able to tell us objectively that whether this value of 0.058 is small enough to be considered as uncorrelated. Whenever the correlation is 0, we say that the two variables are uncorrelated, or whether the value is high enough to conclude that lymphocy and survival month are correlated. Then there could be another problem, even if suppose you say that they are uncorrelated, but the doctors or the physicians have some evidence that lymphocy and survival month definitely have to be correlated according to their expertise. In this case, then what happens? Then that means your data are not good enough to establish that correlation between the two variables. So you have to increase your data points, you have to take a larger sample, and then you have to find out whether the two variables are correlated or not. So all this come under the exploratory data analysis. Slowly you are trying to build your information that you are getting from data and trying to arrive at the meaningful conclusions using the methods in statistical inference. Right now we are again at the nascent stage of just understanding what is the correlation and what does the correlation coefficient means, etc., etc. So we will not bother about these details right now, but you should be aware that in practice, see, the data like this was a cooked up data. I said data like this is not a cooked one, it is coming from a study. So whenever you have a data coming from a practical real life situation, then the data can show any kind of weird pattern which will not fit into your regular that kind of scatter diagrams that we saw in our PowerPoint presentations. They were too simplistic to observe, and then the situations are generally more complicated. You can see a cloud of points here and then some points gathering only on this side, so what to do? So all this will go under the advanced topics of statistical analysis. Anyway, third example, again it's an artificial data, height of a person and body mass index. I suppose everybody is aware of the body mass index. How do you compute that? Weight divided by height in meters square multiplied by 100 or whatever. So here what do we observe? That as the x value, that is height of person, increases, the taller the person, lower is the body mass index. Taller the person, lower is the body mass index. So there is a kind of negative correlationship between the two variables. That's what we observe. But how much? How much cannot be answered by the scatter diagram? How much is answered by the correlation coefficient? So when you compute the correlation coefficient, here it is minus 0.8 and it is quite high because the highest negative value of correlation coefficient is minus 1, and therefore it is a strong negative correlation case. So I suppose these are the three examples which give you the idea about the computation of correlation coefficient and the different situations. Now let us go back to our formula of correlation coefficient in the slide. So this is computing something in the numerator and computing something, two similar quantities for x and y in the denominator. Now here, if you divide by n here, n in the numerator as well as divided by n in the denominator, you will see that this is nothing but the standard deviation of x and this is standard deviation of y. So you are dividing by standard deviation of x and standard deviation of y. And on the numerator, you are having the summation xy minus summation x summation y. So actually this is the joint variation between x and y that you are computing in the numerator, and that is why it is called as product moment correlation coefficient. So here, why we are taking products of x and y? We are not taking products of x and y, we are taking the products of the deviations x minus x bar and y minus y bar. So, in the first quadrant, this is called as the first quadrant, both x and y are positive. Both x and y are positive. So, the deviations, product of the two deviations from their respective means will be positive in the first quadrant. In this quadrant, this is called as second quadrant in coordinate geometry. X is negative and y is positive. So, in this quadrant, the product of the two deviations is going to be negative. This is the third quadrant where both are negative, x is negative and y is negative. So, if you take the product of the deviations, that is going to be positive. Here in the fourth quadrant, x is positive but y is negative, so the product is going to be negative. So, in the sense that first quadrant and third quadrant, the products are going to be positive, and second quadrant and fourth quadrant, the products are going to be negative. So, when you are taking these products x minus x bar and into y minus y bar, and suppose they have this kind of relationship, then there it shows that it is going from negative to positive, and then there is a kind of positive correlation between the two variables. I will not go into further more details about this, but the point is that as in the case of dispersion or variation, we try to compute the average variance between the variable around its mean. Here we are computing the average joint variation between the two variables around their respective means. And then we want one more thing, that if we are suppose measuring, for example, in this case, these are the heights of fathers and sons in centimeters. Instead of measuring the heights in centimeters, suppose we would have measured them in inches. Then should the correlation coefficient change? It shouldn't, right? So, if it should be a unit free quantity, therefore we divide them by the standard deviation, respective standard deviations. So, in order that if we change its origin, it should not get affected, we are taking the deviations around means, and in order that they should be a unit free quantity, we are dividing them by the respective standard deviations, and that is why the formula is complicated to understand, but that is the concept behind this. So, you can try yourself, that you can convert those heights in that example to inches and then compute the correlation coefficient. Talking about any statistical measure, we always talk about its merits and demerits, because the demerits of a statistical measure lead to the further invention of another statistical measure. So, merits determines a single value which summarizes the extent of linear relationship. Everybody will get the same value for the same data, that is the meaning of this. It indicates type of correlation, depends upon all observations, cannot be computed for qualitative data such as honesty and intelligence, beauty and intelligence, etc. Because this is going to be the case of a kind of a categorical variable or qualitative variable, but there is a measure for that which is known as rank correlation coefficient. You can rank the data for the two variables according to the intelligence and honesty in this case, and then you can compute that rank correlation coefficient. I suppose SAS Proc gives that rank correlation coefficient also as one of the outputs. So, the concept and meaning of that is the same as that of the Pearson correlation coefficient. Now, whenever any measure is based upon all observations as a merit, then obviously the demerit walks in, that it gets unduly affected by extreme values. It measures only linear relationship. What does it mean? See, for example, if you are giving a drug to a patient and the amount of drug suppose starts from 5 mg, 10 mg to 15 mg, 20 mg like that, then you get a better and better response up to a certain point. But if the drug is given in excess, then the response could be lesser and lesser. So there isn't a kind of linear relationship. There may be a kind of parabolic relationship, and in that case the correlation coefficient doesn't fare well or doesn't give a good idea. So that is why this scatter plot is very important. If the scatter plot shows some kind of non-linear relationship, then you should not use the correlation coefficient, but you should use some other correlation coefficients or correlation measures, such as correlation ratio is one of the measures. We will not go into those details right now. So in SAS, PROC-COR is used to compute the correlation coefficients, and it also computes 3 non-parametric measures of association and probabilities associated with these statistics. So there is something called as Kendall's law, Hofding's measure of dependence, Pearson's, Spearman and Kendall's partial correlation. They go into the case of qualitative and multiple variables. So let us quickly take a look at an example with the help of SAS code. This is one data. These measurements were made on men involved in a physical fitness course at North Carolina State University. The variables are age in years, weight, run time, time to run 1.5 miles in minutes, and oxygen intake, milliliter per kg body weight per minute. Certain values were changed to missing for analysis. We are going to talk about how to handle the missing data, etc. in our next to that session. So once you use this PROC-COR data fitness plot, matrix histogram, etc. Here we are not plotting the histogram, so that ODS graphs is off. You get, this is the output. It first gives you the simple statistics for all the variables, standard deviation, sum, mean, maximum and whatnot. Whenever you have more than 2 variables, SAS always prints it as a matrix of correlation coefficients. How does one interpret this? Age versus age. Now age versus age, what is the meaning of the correlation between x and x itself? So it is a perfect linear relationship. I told you that in case of any linear formula, for example y equal to 4x plus 9, you are going to get the value of r equal to 1. If it is exactly so. So if here x is age and age, so that means it is y is equal to y kind of thing, or x is equal to x. So for all these diagonal entries you will see as 1 1. These off diagonal entries, this is the correlation coefficient between age and weight, minus 0.23354 is the correlation coefficient. That means there is a negative correlation between age and weight of the person. Age and oxygen intake, minus 0.31474, again a negative correlation. Age and run time, it was the time required to run 1.5 miles. So age and run time, there seems to be a positive but quite moderate positive correlation between the two variables. So in this way you can interpret all these correlation coefficients. These 31, 31 etc. are the number of pairs which are considered for computing these correlation coefficients, and these are some p values. See, probability greater than mod r under h naught rho equal to 0. We will see what are p values and what to interpret from these values later on. Just as for age, relation with each other, you can have weight relation with age, weight relation with oxygen. So weight and oxygen, the correlation coefficient is minus 0.15. One interesting thing you will observe here is that the correlation coefficient between age and weight is the same as the correlation coefficient between weight and age, so to say, or oxygen and age and oxygen. So this is a symmetric matrix. In statistics we call this as a symmetric matrix. This number and this number is same. So they are exactly mirror images of each other. That has to be the situation because the correlation between x and y should be the same as the correlation between y and x. One need not give a priority to which variable you are talking in the first. So bivariate data, the order xy is not that important whenever you are talking about the correlation analysis. The order between x and y becomes important whenever we will talk about the regression between the two variables, and that we will do in our next lecture. So the same data here printed on the slides. It gives you this plot also, so scatter plot matrix. Just as the correlation coefficient, you can get the scatter plot of, for example, age and weight scatter plot looks like this, age and oxygen scatter plot looks like this, and whatever you are having at the diagonal places, it becomes a single variable thing. So it is a frequency distribution or histogram for that particular variable. So what have we discussed today is the correlation analysis and its use in bivariate case only, not in multiple variables. Then the scatter plots and various types of scatter plots, statistical correlation, and the measure of that correlation coefficient is that's Pearson's correlation coefficient, merits and demerits of that coefficient, and an example using PROC-COR in SAS.